to make the study more easy, because see, if I ask you to remember first 20 elements itself, you struggle, isn't it? And remembering 100 plus elements is not an easy task. It's just not about knowing the elements, it's about understanding their behavior, their properties, their uses, how they interact with the other elements, how they combine to form everything, every aspect matters. So, classification of elements is very well needed to have a more synchronized study. Okay. So, one of the few atoms, what we are highlighting here, the first atoms we have is Dobereiner's triad. A triad is a set of three elements. Okay. Triad is a set of three elements where three elements are arranged in the increasing order of atomic masses. Okay. They are arranged in the increasing order of atomic masses. It's observed that atomic mass of the middle element is the arithmetic mean of the other two. What does arithmetic mean? Average. Isn't it? So if I take the atomic masses of the two extreme elements, the atomic mass of the middle element comes out as the average of the other. So likewise, he created successfully only three triads. So it's important to note which triads are they. So why are we taking it up is which are those triads? A set of three elements. So first one is lithium, sodium, potassium, calcium, strontium, barium, and chlorine, bromine, iodine. So these three are important for us. Okay, to note. Is that clear? So this, beyond this, he could not extend his theory, so his concept failed. Next came up the law of octaves. So just like you have a musical note, 7 notes, every 8th note resembles the first note. So when Newland came up with this, only 56 elements were discovered at that point of time. And these are some of these elements displayed here. You can see. So he observed that every 8th element resembled the first element in terms of its property. So clear, it's quite obvious. So fluorine resembles hydrogen, chlorine resembles, how fluorine resembles hydrogen? Can someone tell me? It's a test for you. I can say lithium, sodium you are aware of, but how does fluorine resemble hydrogen? We are saying hydrogen, fluorine, all these are having similar properties.
Noble gases, no?
When did hydrogen become noble gas? Is fluorine a noble gas? Can you give me an example of noble gas?
Argon.
Argon. Anything else?
Helium.
Any noble gas in this chart? Whatever you're saying. The symbol of hydrogen, helium is He. The symbol of what is it? Argon is Ar. Can you see any of this in this? No, right?
No.
Unfortunately, at that point of time when Newland came up with this concept, noble gases were not discovered yet. Okay. And fundamentally, you forgot the question I asked, how does hydrogen resemble fluorine?
Isotope.
Isotopes, dear.
Same atomic number, different mass number.
Come again. Same
Same
atomic
atomic number, different
yes,
mass number.
and different mass numbers. Good. So, when you have same atomic number, can hydrogen and fluorine be isotopes?
Yours was fluorine. No.
I have hydrogen, fluorine, chlorine. We said they resemble each other. That's why they are placed in one column. The idea behind placing this, he was one of us actually successful in arranging the elements in the form of a table. Though we don't call it as a periodic table, but this is one of the attempts, the The advantages or, the merits of this table is that, he places the elements in a tabular form. Much better than what, Dobereiner had tried to attempt. So hydrogen, fluorine, chlorine, they are all belonging to the same column, means they resemble each other. Lithium, sodium, potassium, beryllium, magnesium, calcium, all these, they resemble. They show some similarity in the properties. That's why we are placing the elements in a table. That is what is a basis for classification. Now, I asked you how hydrogen resembles fluorine. Does fluorine resemble chlorine? Do they?
Halogens.
Come again. You're almost there.
Halogens.
Good. Then you might tell me hydrogen is not a halogen. How does it resembling? That is the speciality of hydrogen. Fluorine gains one electron to form F minus. Hydrogen gains electron to form H minus. Hydrogen is diatomic. Fluorine is diatomic. Chlorine is diatomic. All these are gases. All these are non-metals. So does fluorine resemble hydrogen? Hence proved? Yeah?
Yes, ma'am.
Are you getting it, students? So don't come from only one point of view that, of course, yes, fluorine, chlorine are halogens. But when it comes to close resemblance, yes, fluorine is a non-metal, hydrogen is a non-metal, chlorine is a non-metal. There is a similarity even in the chemical nature. There's a similarity as non-metals, diatomic, so many things, all are gases. But what is a mismatch you see? Can you tell me in this table? What is a mismatch? Tell me, children. Any mismatch in this column? The mismatch is in the group of non-metals, where is this metal coming? Cobalt and nickel. In the group of non-metals, oxygen, sulfur, selenium, where is this metal coming? So that's where some anomalies are found, some discrepancies are found. So after calcium, this concept fades. Okay. After calcium, this theory of what is it? Newton's law of octaves, the octave concept is failed. Okay. And furthermore, as I told you, what is that? Neon, helium, all these are missing from this chart. Noble gases were not yet discovered. With the discovery of noble gases, there's a total failure. Students. You can hear me. There's a power failure. Maybe the video doesn't work. It's okay. You can still hear me.
Yes, ma'am.
Am I audible?
Yes,
Yeah,
ma'am.
yeah. Just a minute. Yeah. So is the file visible to you?
Yes, ma'am.
Okay.
Yes, ma'am.
Just a minute. Students. The slight power disruption. Sorry. So these are the limitations. And next is what we got is a Mendeleev's periodic table. This came up, this was the first periodic table, successful periodic table given as a periodic law. What do you mean by the term periodic? Periodic means anything that repeats at regular interval. You must have learned this in physics as a simple harmonic motion also. We call it as a periodic motion. Something which is repeating at regular intervals. Is it clear? So, the first ever periodic law was proposed by Mendeleev. Is a Russian chemist. So he came up saying that physical and chemical properties of elements are periodic function of their atomic masses. So periodic laws are often important. What is a basis for classification is very important for us. That's why we are just brushing through this. Okay. So he came up with a tabular column where it has, 8 groups and 6 periods where he subdivided each group into, if you see your textbook, you'll be finding this into subgroups of A and B. Okay, a further subgroups of A and B. You will be able to, one second, sorry. This is a periodic properties. You have your textbook, students. The periodic table is given in your textbook. You'll be able to see that. So what is missing in that periodic table is everything was going well, but there is an anomaly there. What is an anomaly is, some elements are not placed. Anomalies are something that, we have to make a note of. Anomalies, one second, just let me, sorry. Yeah. What is that you're seeing, students? Okay, let me share this. Can you see your textbook? Is it visible? The table?
Yes, ma'am.
Yeah, okay. So this is how the Mendeleev had proposed a periodic table, the first ever periodic table, proper periodic table, giving, it looks like your Excel sheet, like you have a rows and columns. The horizontal rows are called as a periods and vertical columns are called as a groups. So there's a uniqueness about each cell is that it demonstrates the position of certain elements. So one of the anomalies you find in this, okay, is, elements are subdivided. So if you see tellurium and iodine, can you find tellurium and iodine anywhere? Can you see tellurium and iodine anywhere? Is it visible?
Yes, ma'am.
Students, are you able to see? Are you able to see the periodic table? Can you see tellurium and iodine anywhere? Because sometimes this is emphasized. Are you able to see? See, what is the basis for this is the elements are arranged in the order of increasing order of atomic masses. Okay, so when elements are arranged in the increasing order of atomic masses, you see that elements belonging to the same group will show the same behavior. Just like as we said in case of Newland's law of octaves. So you have, can you see here he has placed all the noble gases in the zero group. And he has placed the elements lithium, sodium, potassium, everything in one group, beryllium, magnesium. It's syncing very well. But when it comes to this particular tellurium iodine, I want to see the atomic masses. See. Why I'm specifying is this is one such unique element pair. We call them as anomalous pairs in Mendeleev's table. Okay. So we should not work on what is common, what is working. So the questions will come from what is not working. So we have to see from the demerits point of view, as far as your competitive exams are concerned. Okay, what do you observe? Are they in the increasing order? You see the rest of the elements, 72.3, 75, 79. Can you see all are in the increasing order of atomic masses? How about this particular pair of tellurium and iodine? No, it's decreasing, exactly. So ideally what should happen? Elements should be arranged in the increasing order. And then we will see the periodicity, that is whether the elements are resembling. But now what happened? Already Mendeleev has placed his elements in such a way that, yes, no doubt iodine resembles bromine. No doubt tellurium resembles selenium. However, is it according to the periodic law? No. That's the discrepancy here. So this is one such anomalous pair. Okay. And even cobalt and nickel is another pair. strictly, nickel has atomic mass of 58.7. It's rounded off and given in this. Okay? Strictly, it's 58.7. This is another anomalous pair you find in this. So what are the anomalous pairs we have here in Mendeleev's periodic table? Tellurium iodine is one pair. Cobalt nickel is another pair. Okay? So the two drawbacks. Okay? I mean, it comes under one category, that it's not arranged in the increasing order of atomic mass. Clear? And what are other demerits here? Demerits is that isotopes don't have proper place here. So if I take isotope of carbon, carbon 12, carbon 13, carbon 14. Now, if I have to take carbon 14, where should I place carbon 14? 14 is a position given here. So is this 14 mass, is it representing nitrogen or should I place carbon here? That means no place for isotopes. Is it clear? So see, if you are indicating a particular element for a particular mass, it should be an identity for only a single element. It should show a uniqueness there. So atomic mass is not a unique property. That's what is being, focus. I mean, that's what we are highlighting, saying that this is a demerit. Okay. If atomic mass had been a unique property, this 14 mass should have been only for nitrogen. No other elements can have atomic mass 14. No, not even isotope. So atomic mass is not the basis for classification. That's totally now ruled out. So which is the only thing basis for classification? It has to be now atomic number. No two elements can have identical atomic number. You have studied no atomic numbers in atomic structure chapter. Do you see any two elements having same atomic number? You say isotope. Sometime back, someone told me isotope. If I ask you isotope, carbon 12, carbon 13, carbon 14, all are isotopes. They have same atomic number, different mass number. But don't they represent the same element, carbon? Are you getting it? So isotopes, when I say it represents the same element. So atomic number is a unique feature. Just like you have an Aadhaar card. That's identity. Now everyone is knowing, even a just born child also, I think will come up with an Aadhaar card as an identity. Isn't it? So no two people will have same Aadhaar card number. So no two elements can have same atomic number. Clear? That's a unique property of an element. So isotopes did not have place here. Another discrepancy came is with hydrogen. Hydrogen has no proper place. Poor thing, it's wandering around. Should I go with halogen or should I come with lithium? Okay, hydrogen has a property of losing electron as well as gaining electron. If it loses electron, it is like sodium. If it is gaining electron, it is like fluorine. Just now I said some time back. So where should hydrogen be placed? So there is no proper position for hydrogen. There is no proper position for isotopes. There is no, the anomalous pairs is another drawback. So all these are the demerits. Then if I have to speak about demerits, what are the advantages? Why are we speaking about this table? Yes, he was successful in demonstrating a periodic table fitting in 65 elements. That was a great achievement. 65 elements were accommodated, though there were some flaws. Right? Another thing is, the beauty of this is, he gave place for the newcomers. What are the newcomers? The elements which were not discovered yet. So he said, okay, even if someday, one day the element is discovering, someone is discovering the element. So let me give some position in the periodic table. He said, Eka. And he gave a position. What is it? Eka. When I say Eka boron is aluminum. Eka silicon is germanium. Eka aluminium is gallium. Note these names. These are probable questions. What is this Eka? Eka. It's coming from derived from Sanskrit prefix. Eka means something which is resembling. It is like. Okay, so Eka boron, element resembling boron, Eka silicon, element resembling silicon, Eka aluminium, element resembling aluminium, which were later discovered as, gallium as Eka aluminium and germanium as Eka silicon. Okay, can you see? Got it?
Yes, ma'am.
Now our modern periodic table. So what is that is replaced modern periodic table? Masses replaced by atomic mass is replaced by what? Atomic number. So why have they taken atomic number? Because the X-ray spectrum is something that you have to focus. What is the plot? The plot is root nu versus Z. So when we plotted root nu, what is nu? Frequency of X-rays versus Z. It is a straight line, okay, passing through origin. So indicates that this is directly proportional to atomic number. And it's again indicating that atomic number is that unique property which is the identity of an element. It's not atomic mass. Is it clear? So, physical and chemical properties of elements are a periodic function of what? Atomic number, not atomic mass. Okay. So, how many elements are there in this periodic table? Do you know how many elements are there in this periodic table?
118 elements.
Good. Okay. So, elements are classified into how many periods and how many groups?
7 periods, 18 groups.
Yes. So, it's important. What you need to know is, if I tell you an element atomic number 25, you should be in a position to tell me which period, which group. That is your mastery needed. Okay? It's not as simple as anything. It's the mastery level needed is if I tell you atomic number. So for that, what we frame here is you have to know each element is, each period begins with which element and ends with which element. That range is very, very important. Is it clear? That's the way you have to learn it. Got it? So each period, if you see, the first period belongs here, we have only 2 elements, hydrogen and helium. Okay. Then second period is ranging from lithium to neon. See, look at the range. If I have to tell you hydrogen, helium, it's ranging 1 to 2. Next second period is ranging from which one? Period starting from 3 to ending with 10. And third period starting with 11 ending with 18. Fourth is 19 to 36. Fifth is 37 to 54. Sixth is 55 to 86. Seventh is 87 to 118. And I want you to consider the difference between this. The difference in the atomic numbers. What's the difference in the atomic number? 3 minus. Yeah, or 10 minus 8. Okay, 3 minus 1 is 2. That means the first period has only 2 elements. The second period has how many elements? 8. Third period has how many elements? The difference is 8. Then fourth has how many elements? Fourth is 2, 8, 8. After that, the difference is what? 36 minus 8, 18 is 18 again. 54 minus 36 is 18. 86 minus 54, 32. 118 minus 86. How much? Again. What's the difference? 118 minus 86. Is it that difficult? Again, 32 elements. So This 2, 8, 18, 32. We call them as magic numbers. Okay. We call them as magic numbers. So if I ask you an element with atomic number 48, belongs to which period? Right? That means 48 should belong to this. So an element with atomic number 48 will belong to the fifth period. An element with atomic number 92. I just asked you period. I didn't ask you group. Which period? Atomic number 92. 92 falls in which range?
87 to 118.
Ah, good. So which period?
7 period.
7 period.
That's the period. So can you see now? Atomic number 56. Yes, 56 is sixth period. Absolutely right. Okay. So this is the way, you don't have to by heart the table. Please let me tell you. Okay. If I know the range, the first element and the last element, I know from this atomic numbers, where can this particular element be placed? Is that clear? Is that understandable, students? Okay. Right. So let's just go. This is one thing. And you have to, yes, one thing you have to remember is at least remember the first 4 periods. I'll say mandatory up to atomic number 13. Mandatory. It's a must. If I tell you which element is placed where from 1 to 30, you should be in a position to give me there is a period and the group number. Like if I wake you up in the sleep and I just tell you where is manganese, I should be in a position to tell me that it belongs to 4th period and it belongs to 7th group. That should be the level of preparation. So you don't have to by heart the entire table. At least know for first 30 elements. First 30 elements positioning is very, 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 very important. You cannot go wrong here anywhere. It's a must. How will I remember? You should be in a position to, remember this, you know the first 30 elements, right? First 30 is important for atomic mass, atomic number, electronic configuration, and their positions. Is it clear? As long as you remember your name, you remember this first 30 elements. I'm telling you. The ones you start by hearting it now. You'll never forget. Because we never forget what we learned in our childhood. So definitely this will be in your memory. First 30 elements is mandatory. Okay? So if you know this position, automatically you can replicate the remaining. First 30 you keep in mind. Is it clear? So let me take up in first 30. Right? Let me take nitrogen. Where is the position of nitrogen? It is atomic number 7. Which period, which group? It belongs to 15th group and it belongs to 2nd period. Isn't it? So can give the atomic numbers of the subsequent elements. Can I give the atomic number of the subsequent elements? Its atomic number is 7. It belongs to 15th group. What will be the atomic numbers? Which period does it belong to? I told you 2nd period. So can you see the differences? Use the magic numbers. 2, 8, 8, 18, 18, 32, 32. This is the order we gave, no? So your 7 is belonging to your 2nd period. So what should be the atomic number of the subsequent element? 8 plus 8? So, 7 plus 8?
15.
After that, what should I add? Which number is coming? 18. So when I add 18, to this. What is the next? 33. Then add another 18 to this. What do we get? Yes? 51. 51 plus 32. What do we get? 83 plus 32. You'll get the subsequent element. Don't you see the same thing in this? Can you see the atomic numbers?
Yes, ma'am.
So, the range will give you an idea which element can be placed in which particular period, as the exercise we did. So, if you remember the first 30 elements, you will be thorough with the atomic numbers, you'll be thorough with the position, the period, and group number of that particular element. So you can subsequently use these magic numbers 2, 8, 8, 18, 18, 32, 32 to generate the atomic numbers of the remaining elements in that particular group. That's the magic. Clear? Is that understandable?
Yes, ma'am.
So this element, this periodic table, can I say it's a periodic function of even electronic configuration? Can I say physical and chemical properties are periodic function of electronic configuration?
Yes.
Why? Because when atomic numbers are unique, electronic configurations are unique. And this periodic table is also called as a Bohr periodic table. You know? Why? It replicates your Bohr's model. See? What does Bohr's model have? It basically emphasizes on your shells. Bohr came with the concept of shells. So, look at this. The first period, you have only 2 elements. Can you see that? Second period, how many elements? See, 3 to 8, 10. So, can you see the second shell is being filled? In the first period, the first shell is being filled here. 1s1, 1s2. Second period, 2s1 to 2p6. The second shell is complete. Then third period, what is happening? It's also replicating your off-Bohr principle. 1s2, then 2s, 2p, after 2p, 3s, then 3p, after 3p, then you get 4s. Are you able to get that? The 4p is getting filled. So when you start with the first member, you will see that the electron is, you will have the ns1 configuration, and the 18th group, you have ns2, np6. That means every time you are moving across a period, the electrons are filling up in the same shell. You're beginning with a new shell, and the outermost shell is getting the octet configuration ns2, np6 with the 18th element. Is it clear? ns1, and then you complete the shell, you complete that period with ns2, np6. You begin with ns1, you complete with ns2, np6. Do you see this? 3s1, 3s2, 3p6. 7s1, okay, let me take 6s1, 6s2, 6p6. Okay? Is that clear? So every shell is getting completed. Every period begins with a new shell. Okay? Every period ends with the octet configuration of the shell. So period number is equal to what? It's equal to the valence shell or the number of shells. Are you getting it? See, what is a valence shell? 4d1, 3d1, 4s2. What is a valence shell in this? An element is having an electronic configuration 3d1, 4s2 now. Which is the valence shell here? How do you find out the valence shell, students? If I asked you one question. Can you tell me what is a valence shell in this configuration argon 3d1, 4s2?
Is it 2?
Come again?
Is it 2?
Okay, what do you mean by valence shell? Are you hearing this word first time? No, please students, don't have to refrain. Please, if it is the first time you are hearing, I will explain you what is valence shell. So please be open to the conversation. How many of you don't know what is valence shell?
Students, tell me what is
Please, you can admit
electron?
students. There is no point wasting our time in thinking and assuming. It's better admit, ma'am, I don't know. Please explain me. In one word.
Shell of an atom.
So why do you call it valency? The word valency, you know? Because the outermost shell is a valence shell. So valence shell is nothing but outermost shell, students. That's why the electrons in the valence shell will give valency. Are you able to get it?
Yes.
Is that clear?
ma'am.
Please
Yes, ma'am.
get used to the new terms in case you're not used to it. Is it clear? Because we come across these terms. Yeah, students, anyone having a doubt? Somebody? I felt like someone called me. Nobody? Yeah. Shall we proceed? So now in this, what is the outermost shell?
4s. 4s.
Shell. Is S shell?
So the fourth.
Correct. Yes, get the distinction very clear. Very good. So fourth shell is a valence shell. Fourth shell is also the outermost shell. Outermost shell is equal to valence shell. Put it like an equation for you. Okay? Got it? So fourth. So what did we say? The period number is indicating number of shells, or it's also indicating the outermost or the valence shell. Okay. So what is the valence shell we said in this? It's 4. So where does this element 3D14S2 belong to? Which period does it belong to? It will belong to the 4th period. Is that clear? Are you getting it?
Yes, ma'am.
So an element is having an electronic configuration 5D3 6s2. Okay. Okay. Xenon 5D3 6s2. To which period does this element belong to?
6 feet.
Good. Why? Because the outermost
Because
shell or the so-called valence shell is the 6th shell. So from the configuration, you can make out that's the basis for arrangement. So the elements having the outermost shell of the element represents a period now, in other words. Okay. Is that clear? So period number is also indicating the total number of shells or the outermost shell. Fine. And every element in a period, what happens? Electrons will fill up the same shell. And the difference in atomic numbers as we progress will be a difference of only 1. As we progress, 19 to 20, 20 to 21, a difference of only 1 atomic number you see when you move from left to right. That's the important feature of a period. Now coming to group. Yes, just now I said. What is it? Group, they will have same valence electron configuration, valence shell configuration. Again, what is valence shell? What is valence shell?
Outermost shell.
Yes, you should not forget this word.
Outermost
Valence shell is outermost shell. Is it clear? So valence shell electrons will remain same. Therefore, the elements of the same group will have same valency. For example, look at this lithium, sodium, potassium, rubidium, cesium, francium. What do you observe? Everything is having NS1. Isn't it? So when I take this particular element, all elements in a group will have same. Can you see NS2, NP1 in group number 13? Can you get that? So basically your identity periodic properties are one hand. But here, the way you arrange the elements, the design of your modern periodic table is very, very, very important. The features are very important. Okay. Is that clear? So NS2, NP1, all elements will have the same. So what would be probable configuration of 113? Can someone tell me? What would it likely to be? Come on. Boron 2s2 2p1, 3s2 3p1, 4s2 4p1, 5s2 5p1, 6s2 6p1. Then what should be 113?
Seven, yes.
Come again? Yes. 7?
7 is to 7 P1.
Yes. Are you able to get that now? Is it clear? See, you don't have to by heart all these configuration, students. Okay. So tell me, I gave you 113 belong to which period?
7 period.
7th period. Am I right? And I'm saying it belongs to group 13. What's the general configuration of group 13? I will come to know from boron. I don't have to remember everything. What is the outer configuration of boron? I told you, right? 1 to 30, you have to remember. It is 2s to 2p1. So then 113 should be 7s to 7p1. Isn't it that simple logic works? It's something, whatever is there, you extrapolate it. Clear? Got it? See, an element with atomic number 116, it belongs to which period?
7.
7th period, and it belongs to 16th group. Shall I tell you another magic? See these numbers. 113, 114, 15, 16, 17, 18. Can you see? What are the group numbers? 13, 14, 15, 16, 17, 18. Can you see some relation there? What is it? Group number minus 100, no? Are you able to get that?
Yes, ma'am.
So for some groups only it's applicable, not all groups, of course. See, even your third period elements also same thing. See, 13, 14, 15, 16, 17, 18, the group numbers and the atomic numbers are same. Okay. So now what will be the configuration of this? Can you tell me? 7th period, 16th group. 16th group, what is the general configuration? See, no, your first element of the 16th group, you have oxygen. I know oxygen is 2s2 2p4. Am I right? So what would be the configuration of 116th element?
7s2 7p4.
7s2 7p4.
Excellent. Can you see? Okay. So simple, you just elevate your thought, project it, we'll get it. Understand the basics, you will be able to answer. It's not any rocket science. Clear? Okay. So are you clear with this? And now, then we have something called as, no, it's very clear. You have the basic periodic table here. I've told you about everything. But you can see there are two separate series just below. We call them as lanthanoid and actinoid series. So what are the elements of lanthanoids? Lanthanoids are the elements following lanthanum. Okay. So after 57, if you see, 58 to 71 are separately placed, and 72 onwards, it's merging with the 6th period here. Okay. So elements 58 to 71 are known as lanthanoids. We also call them as the 4F series. Okay. And elements from thorium to lawrencium, 90 to 103, they follow actinium. See, after 89, 90 to 103. And again, with 104, it is falling in the adjacent position to actinium. So, elements following lanthanum are lanthanoids. Elements following actinium are actinoids. I just want you to observe this pattern here. Sorry. I want to observe this pattern here. What is it? After 5D, can you see, observe this? 5D1, the electrons are entering 4F. Okay. So, what is the maximum capacity of 4F? How many electrons can an F subshell accommodate maximum?
14.
14. So, there are 14 elements. Okay. So, once those 14 are filled up, then 72 onwards, it's merging back with the sixth period. Then 90 to 103, again 14 elements. So this 4F subshell is being filled in lanthanoids and 5F subshell is being filled in actinoids. So can you tell me, looking at this configuration, lanthanoids should belong to which period? I told you the logic sometime back. Come again? Sorry, I didn't hear. Someone said.
Sixth.
Sixth. Why is it sixth? Why is it sixth? You can answer. You must be audible. You can hear me. I'm sure. Can you? Sorry, students, a lot of power fluctuation today. Can you hear me? To which, why does it belong to sixth period? What is the reason you told me? So that you can explain your friends also. They will know the logic.
Who answered, guys? Was it Enoch?
Come on, child.
Ma'am was asking a question, right?
Can you hear me, students? Sir, am I audible?
Yes,
Yes,
okay.
ma'am.
You are.
Okay. Because of this internet disruption, sometimes power fluctuation, I just have a doubt whether internet connectivity is good or not. Yeah. Come on, students. Your answer is right. My question is why? You said belong to sixth period. But why?
Because it was part of this.
It's a part of sixth period. What basis are you telling me this? The answer is not
Comes after
satisfactory.
50. It,
Correct. Okay.
comes.
See, for that matter, after 86, 87 is coming. Isn't it 87 is belonging to seventh period? Same logic doesn't work here, right? That logic doesn't work every time. Isn't it? After 2 element is 3. 3 belongs to second period, but helium belongs to first period. Yeah. I appreciate your attempt. You are correct. Your answer is correct. But the reason, see, sometimes, we have to check for the reason, child. That's the reason I'm asking you the reason. They will give you the reasons. You have to choose the appropriate reason. Your answer may be by fluke correct, but the reason is missing. Okay, I'll give you a hint. Focus on the configuration. The configuration of lanthanoids is given. I circled it, see. What is given? 4F, 5D, 6S. So, which is a valence shell?
6. Yeah, well,
Come on.
Six.
6. So, means which period? Sixth period, no?
Yeah.
So, all the lanthanoids belong to sixth period. Why? Why? Because their valence shell is the sixth shell. Not because 58 is following 57. Okay? Is it clear? Good. I appreciate your attempt. But is it clear? Start thinking. You're not wrong. Start thinking. Start exploring. This is the way you explore. Okay? Clear now? So actinoids belong to which period? Actinoids belong to which period?
7th period.
Logic. Come on. Which period?
Seventh
Valence shell
period.
is
Why? Why?
valence shell is 7.
Because
The valence shell is
the
7.
valence shell is the seventh shell. Excellent. Excellent. So lanthanoids means the period number is 6. Actinoids is period number 7. Now, to which group do they belong to? This part you will be doing big time in your nuclear physics when you do emission, beta emission, all that you'll be doing in physics. We'll call it as a group displacement law. You do all this in physics or nuclear chemistry also if you're doing it. There, this part is going to help you. Okay? To which group number? So, if you see here, what is common you're seeing is, can you see 5D1, 6S2, 6D1? So in general, the electronic configuration is N-2, F1 to 14, N-1, D0 to 1, NS2. This is the general configuration of both lanthanoids and actinoids. Okay? And see, as far as what is the speciality of group numbers? I'll just wind up in 5 minutes with the students. Okay? What is the speciality of group number? The group number, it highlights the valency or valence electrons which participate in chemical reactions. Okay. So when you see N-1 and N-2. So I have 6S, 5D and 4L. Do you think the 4F electrons which are deeply buried in the shell, will it come out to take part in reactions? Do you know? Which electrons easily take part in chemical reactions?
The valence shell is not.
Outermost shell. Some extent, we call it as a penalty weight shell, N-1 shell. Okay. Now, electron from 4 taking part in reaction is something that's not happening often. It's difficult. So, which electrons will take part in chemical reactions in these lanthanoids or actinoids? Only the valence shell and the N-1 shell. So 6S2, 5D1 will be taking part in reactions. So which one is fitting with the 6S2, 5D1 configuration? Is it not the group number 3? See here. Same thing, even your actinoids. What is it? 5F, 6D1, 7S2. Even if I pick 6D1, 7S2, that is again belonging to group 3. So lanthanoids and actinoids both belong to which group? Group? What's a group?
3.
It's group 3. Something, unique feature of lanthanoids and actinoids is these elements which belong to two or four elements belong to the same period is fine, makes sense. But all belong to the same group. Isn't that unique? See, elements, rubidium to xenon, they're all belonging to the fifth period. It makes sense. But individually, 55, 56, 57, 58, all are belonging to different groups. But how is this? 14 elements of lanthanoids belonging to same period. And they also belong to the same group. That's why they didn't have place in the mainframe. It's separated out from the mainframe. Is that clear? So this is something you have to hold. Okay?
I'm sorry to interrupt. Hello.
Ma'am,
could you repeat this because your voice was breaking? I think. Yes.
Okay. See, students, let me get back to this once again. Focus on, did you understand that the 4F electrons cannot take part Only the 5D and 6S will be maximum taking part in reactions, because 4F is, we call it as a n minus second, or we call it as anti-penultimate shell. It's buried, so they don't take part. Same thing when I have 5F, 6D, 7S, 6D and 7S electrons. 5D1, 6s2 electrons, they take part in chemical reactions, not the 4F and 5F. So, on this basis, to which group do these lanthanoids and actinoids belong to? They both belong to group 3. Because they all have the same configuration, N-1 D1 NS2. So, that's the reason they belong to the group 3. As far as period is concerned, it's the 6th period. As far as actinoids concerned, actinoids belong to 7th period. What I'm saying is, if you take an element belonging to same period, yes, definitely, consider the 4th period. From atomic number 18 to atomic number 36, all these elements belong to the same period. But isn't it individually every element belong to different groups? Are you able to get that? Potassium, group 1, calcium, group 2, bromine, group 17. Isn't it? Individual elements are belonging to different groups, but all the elements belong to same period. Now look at the pattern, what we have in lanthanoids and actinoids. What is it? Cerium to lutetium, 58 to 71. Which period? 6th period.
Group.
Which group?
Third group.
Which group? Third group. Isn't this unique? All the elements are belonging to same period. All the elements are belonging to same group. Now, where will poor Moseley take a position to accommodate all these elements in the main frame? He will not have. Unfortunately, that became the drawback. That the lanthanoids and actinoids are not given a proper place in the main frame. This is the reason. Understood? Is it clear? So this is important. Group 3, please mark my words. Your physics, they will be somewhere, maybe you're connected, nuclear chemistry is coming up, they will see after beta emission, the group number change, we call it as a group displacement law. There you will see this, the group 3 coming up, playing a vital role. All the lanthanoids, all the actinoids belong to group 3. Okay. Whereas individually, lanthanoids 6th period, actinoids 7th. Of course, you must be knowing the SPDF. I hope you are clear. You must have, right? S block elements, P block elements, D block elements. These are the highlighted features you have to remember as far as your periodic table is concerned. So tomorrow, we will just quickly go through the periodic properties. Okay? Mainly what you have to remember. Then we'll follow up with the numeric. The questions. Fine. Yes, sir. Shall we wind up? Is that okay?
One thing which I wanted to mention was they are aware of S subshell, P subshell, D subshell, and X subshell, but then they are yet to know about S block, P block, D block, and F block.
No, that's what I'm saying. If you don't know, we will go ahead. No problem, student. See, assumption is not good. If you don't know, please stop me and you ask. Is it clear? Because without knowing the basics, there is no point moving ahead. Basics fundamentals are very, very important for us. Okay. We'll do that.
Sure.
We will go through the SP, D, and F block elements, then we'll go to periodic properties. No problem. Okay, sir.
Excellent, ma'am. Thank you so much.
Yeah.
Excellent students.
Okay.
All the best. I see most of you on videos. Very good. Some of you have not been on videos. I want everybody to be on videos from tomorrow. All right.
Excellent. Sir, I have something to say, very important. Again and again, I've been repeating.
Please, ma'am.
Because this is the basis for their entire inorganic chemistry. Complete chemical bonding cannot be done without this chapter. And the basis for this is your electronic configurations, your knowledge of electronic configurations. So as I told you, 1 to 30 is mandatory. Have to keep it, please.
Students,
because more you are prepared, students, that's very important.
Students, as madam mentioned, already you have already done the assignment of doing the electronic configuration in detail from elements number 1 to 30. I want you to repeat that before you come for tomorrow night's class. All right. And be thorough with the electronic configuration of.
Exactly. That will become the basis for us tomorrow to go with the topics. Yes.
Sure.
Yeah. Any doubts, children?
No, ma'am.
No, ma'am.
Yeah.
Excellent, students. So good night, everybody. Thank you so much.